I'm Bhavedhir V. Bharadwaj. Welcome to episode 18 of Genesis of Tomorrow. The following is a conversation about quantum information theory, quantum simulation, and more with Dr. John Goold, a professor in physics at Trinity College Dublin. Also, 86.1% of you watching this have not subscribed yet. So, folks, if you get even the slightest bit of value from our show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. Right?
Sure.
Okay. So, people do realize the basic crux of what quantum mechanics generally might be able to achieve in different areas, but what are some the less obvious facets of the applications of quantum mechanics?
Um, I would say that I find it interesting that people are always kind of go straight to applications of quantum mechanics, because I mean, quantum mechanics has been around for 100 years, and I mean, nothing has really changed with the theory. I mean, it's a theory which is sort of fundamental in physics. It describes, you know, matter. In a very accurate way. I mean, it's responsible for the explanation of much of the sort of known phenomenon that we have in material science and chemistry um, across the board. Like, but I guess what you're insinuating by your question is perhaps to do with the sort of relatively recent interest in quantum technologies like quantum computing, quantum sensing, quantum communications, which are all in various different levels and degrees of sophistication. For example, there's a lot of interest at the moment in quantum computing. A lot of venture capital has flown into various different companies. There's a lot of multinational sort of interest in developing quantum computers, but there's yet actually to have there's like yet any demonstration of a useful sort of quantum advantage, and it's still an open question as to when and where that application will emerge. But I think maybe your question was about where else do you see sort of unforeseen applications of quantum mechanics. Um, so from a technological perspective, I mean, it's a very difficult question, right? Because I mean, quantum mechanics is kind of a universal theory. I mean, it's the best theory that we have at the moment until one day perhaps another theory supersedes it, like happened with classical mechanics. But I mean, I don't really know the answer to that question, if I'm honest.
How about if we tweak this entire approach? What you personally, on a personal level, are most intrigued
I'm
in
actually
quantum
interested in the
mechanics?
opposite question, which is why, I mean, people are often kind of concerned about what are the kind of applications of quantum mechanics or the quantum world in general, and the different things that that tells us about the nature of reality. But for me, an interesting question and a question that kind of permeates my own research topics is, how does the classical world emerge? I mean, we don't experience quantum mechanics in our everyday life. We don't need it to describe the world around us, really. For the largest part, we can do just fine with classical physics. And actually, given that that all of the evidence points towards quantum mechanics as being a kind of theory which incorporates classical mechanics, then why is it so difficult for us um, to actually observe quantum phenomena and for it to be kind of relevant, given its sort of pervasive nature?
And what have you found out in this research area of yours?
Well, I mean, there's various different facets of it. So one of the things that I'm really interested in is kind of sort of statistical mechanics and thermodynamics. So, in particular, thermodynamics. So thermodynamics was a pretty kind of pragmatic theory. It sort of originated in the 19th century, and largely speaking, due to capitalism. We had the Industrial Revolution and also wars, and people wanted to sort of make machines so that they could sort of get rid of expensive labor. and people started to think about energy because, I mean, energy is a concept that's so basic in physics. I mean, if you think about it, right, what's kind of amazing for people sometimes to hear is that prior to kind of the mid 19th century, humans didn't actually have any, there was no meaning to the word energy. It didn't exist, right? People had a different idea. For example, heat up until quite late in the 19th century was thought to be a fluid called phlogiston, and people didn't even know the first law of thermodynamics, which is the sort of explains to us how you can interconvert different forms of energy, work and heat. So work being kind of useful energy and heat being a kind of byproduct. Um, and thermodynamics then started from various different there's various different players in the story, but I guess people started to think about that sort of interconversion of different types of energy due to industrial revolution. And also Carnot, which was a French military engineer, was kind of humiliated by the fact that France sort of lost in the Napoleonic Wars to Britain, and he sort of wanted to understand why Britain were so successful, and he said that they had the steam engine, and he wanted to understand how the steam engine works. So he started to think about it and came up with this idea that what is the ultimate efficiency of such a device, and that led to a very fundamental law in physics, which is the second law of thermodynamics, which was later formalized by people like Clausius, etc., in the latter part of the 19th century. And for the first part of that sort of story, thermodynamics was kind of largely seen as a kind of, let's say, phenomenological theory where you really kind of think about laws in an empirical way and apply them to realistic situations. And it kind of, you have to understand that in that period of time, they didn't even have the concept of an atom. So they didn't really understand that the laws of physics can emerge, like thermodynamic laws can emerge from the aggregate behavior of many particles, which is then leading to the development of statistical mechanics by people like Boltzmann and Maxwell, etc. So they wanted to understand how sort of gas laws, like the ideal gas law, etc., emerge from thinking about matter as being comprised of atoms. This is already before quantum mechanics was discovered. The idea of an atom was there, right? So the idea of an atom goes back to the Greeks, but it was kind of brought again to the surface by people like Boltzmann. And the big triumph of Boltzmann's theory is that he was able to understand the emergence of these phenomenological laws of thermodynamics, which are, you know, there in physics from microscopic principles. So he could understand, and we could understand following the development of statistical mechanics, how thermodynamic behavior emerged due to the aggregate behavior of many particles that comprised a solid or a gas. Okay, and that's kind of in a nutshell this sort of thing. And then you ask yourself, okay, but you've mentioned nothing about quantum mechanics. Where does quantum mechanics come into the fray? And we have to remember exactly how quantum mechanics was discovered. Um, so actually, it was a mistake, right? It was a mistake. It was initially Max Planck was doing a PhD thesis, and he was interested in a particular problem, which was this problem of black body radiation. So you want to understand how kind of light is absorbed, and there was an anomaly when he was trying to apply the Boltzmann theory. So this idea of statistical mechanics, which you're able to understand things like energy very well in solids. So they couldn't understand why Boltzmann's theory, which was the best theory of the day, wasn't sort of fitting the experimental observations. And in his thesis, actually, it's quite famous. There's a quote where he really says in German, in an act of desperation, I let energy be quantized. So he really just said, well, look, I've tried everything else. The thing's not working. Let me now allow energy to be absorbed and emitted in discrete units or quanta. And all of a sudden, his theory started to fit the observed experiment. So it was a mistake. Okay. And actually, it's interesting because these mistakes that led to quantum mechanics were actually mm, kind of had their origins in thermodynamics and statistical mechanics. So I would argue that thermodynamics was very important to bring about quantum mechanics. Of course, the theory of quantum mechanics was later formalized by people like Heisenberg, Dirac, Schrödinger into a sort of a well sort of oiled machinery to do calculations, and you had all of the formal mathematics and Hilbert space, etc. Operators came later, but the initial observations by people like Planck and Einstein were really motivated by sort of thermodynamic reasoning. So I'd argue that sort of quantum mechanics was kind of born out of thinking about sort of the energy interactions at sort of different scales. Um, and I mean, for me, this is still an interesting question, which is, you know, given now that we know that, the most accurate description we have of the laws of physics is quantum mechanics, how can we understand, as we scale a system up, how the sort of predictions of quantum mechanics kind of tell us how classical systems behave in the limit of large n, okay? So large number of particles. So this is very much something that I'm personally interested in. I think there's various different facets. So one of them is you can go the opposite direction, which is, okay, let me start to decrease the system size. And at what point do I see quantum mechanical features like coherence, superposition, entanglement, etc., emerge? And when do they become operationally relevant for the processing of sort of energy, right? So that's one side of things, and the other one, of course, is something I haven't mentioned, which is the kind of link between thermodynamics and information theory. So one of the interesting things we know now is that there's kind of very nice sort of interplay between information theory, which is abstract and supposedly independent of laws of physics, and actually energy. So this was already again brought about in the development of statistical mechanics by the concept of Maxwell's demon, and people are now asking questions and have been asking questions for quite some time about these type of scenarios when you have a kind of fully quantum mechanical setup with all of the nuances that brings from measurements right to sort of from the act of measurement right to the act of writing onto a memory to erasing information, etc. And these are all of sort of topics of my own research agenda that I like to think about.
I'd love for you to go a little deep into your research area in quantum information theory, but before that, it's interesting to see how theoretical predictions aren't always what inform or ignite the experimental validations. Umpteen times it's the opposite as well. Sometimes you are performing an experiment and something happens, and you carve out a theoretical explanation to fit that result.
Mm,
What,
yeah.
yeah, what is your view upon this? This
I mean, this is
symbiotic
still very
relationship.
this is a very very good question, right? So, you know, there's a modern tendency, I think, in physics, which is really bad for physics, um, which is to, as you said yourself in your own words, to allow experiments validate theoretical predictions. I mean, in my mind, this is actually anti-science. I mean, it's correct that it is science, but somehow, it's not the flavor of exploration that we would like, because in my mind, experiments have to drive physics. They have to drive fundamental physics, right? So, okay, lots of clever people, lots of clever theorists around, and let's set up an experiment to verify the theories. I mean, it's kind of boring, right? What you actually want is an experimental setting that shows you something that you can't predict as a theorist, and then you have to build an explanation. And I think this is where good science comes, and I think there's a modern tendency to do the opposite way around, like you mentioned. I'm not sure exactly where that comes from, but I don't see it being a particularly good thing for science in general, right? Because it's kind of boring just to make experiments to validate theory. I mean, I'm guilty of it myself. I have been involved in projects like that, and they have a place, right? So, for example, with quantum simulation, which is a topic I'm very interested in, which is the idea that you can use kind of highly controllable quantum systems to model quantum systems, because quantum systems of many particles are notoriously difficult to model on classical computers. So, I mean, of course, it's important to have benchmarks that you perform a certain simulation which the answer is going to be to verify that your device is working properly. And I think that's very important and it has its place. But I think ultimately new physics and new science comes from anomalies and experiments. So really, experimentalist does something and has a result and there's no explanation, and then this is the only way we see new physics. And in some ways I think this the tendency to go the opposite way has put us stuck a little bit. Physics is a little bit stuck in particular. I mean, what's remarkable at the moment is the engineering aspect, say in quantum mechanics, like the fact that nowadays we can really manipulate quantum systems over timescales, which would be typically unprecedented, say in condensed matter physics, and in we have very accurate control over them, and that's really brilliant. We can do measurements, we can do all sorts of wonderful things in the lab, but somehow conceptually not much has changed, right? I would argue that not a huge amount has changed. We've got very good at describing quantum systems, but it's not like the revolutions we saw in physics in other parts of the century, like the early part of the 20th century with the advent of quantum mechanics. Like, we haven't had anything like that in physics, really. That's not anyone's fault, but maybe this idea of setting experiments to validate theory up is a contributing factor towards that nothing really interesting at a fundamental level is really happening. I mean, people will argue that, of course, there are very interesting things happening. I'm just talking like maybe there's been no big paradigm shift, I would say, in the last 100 years. I mean, quantum mechanics is exactly the same. You take Paul Dirac, who was one of the founding fathers, you take his textbook, and it's still a perfectly good textbook today. You can learn from that. I mean, in fact, I studied from it myself when I was in university. So, it's not like we've radically altered our perspective. What is new is the engineering aspect, and quantum computing advances towards that, the technological achievements, and what we've learned by kind of setting down the road of attacking that kind of problem, I think, is very valuable. But maybe I'm being too harsh on everybody.
No, I mean, I get it. Sometimes it's a little hard to strike that fundamental balance between the two approaches, and inadvertently so, both are seminal to one degree or the other to drive that scientific innovation to certain extent. And you're very right about how currently the engineering aspect, the engineering side of things, that is probably taking a more, that side is where the foot has been on the gas.
Yeah, yeah, and I
So
mean, and rightly so, right? I mean, the things that
hmm.
people can do in labs now is really incredible, and even the scale of advance over even a period of 10 years is kind of remarkable, and I think that's brilliant, and and that's the reason why it's exciting to study these things at the moment. But maybe I'm a bit being maybe I'm just being a little bit controversial, but I still think there is a big scope to do experiments which, for the sake of doing them, right? And it's always interesting if something comes up which doesn't have a theoretical, prediction, right? Or there's no even way of numerically modeling it. And then I think you're really in an interesting territory. And the hope with quantum computing is that we'll be able to attack problems where not only do we have no theoretical understanding, we have no perturbation theory, nothing like that, but also there's no way that we can conceivably classically simulate them. And I think that that sort of era actually, at least for academic problems, is not too far away. I would say we're really almost there now in terms of technology. Even in near term quantum computing, I see problems of academic interest um, being tackled currently, which are at the borderline of what can be simulated classically. And I think that's a very exciting time to be doing this sort of research, right? So, I mean, just my own research kind of, I have sort of multiple interests, but I would say on one side, I'm interested in kind of the interface between thermal behavior, thermodynamics, and quantum dynamics. And on the other hand, I'm also very interested in sort of quantum simulation and many-body physics. So I have these two angles in my own research, and sometimes they intersect, sometimes they don't.
Talk to me about two things in particular. First of all, quantum information theory. what it is, a basic gist, and then what kind of progress we have been making onto it, and then how about we move on to talk about your work and your in general research in quantum simulation area and many body physics.
Yeah, yeah, sure. I mean, I can tell you a few things that I'm interested in. I mean, first of all, I mean, I wouldn't consider myself to be, strictly speaking, a quantum information theory person. I mean, I do tend to work with a lot of quantum information theorists, and I have worked in groups that are specialists in that. I mean, the basic idea of quantum information theory is I guess on one hand, it's become very broad and as a topic now, but I mean, ultimately, information theory was, I mean, it was kind of 50s Claude Shannon, who was an MIT engineer, um, and he was interested in pretty pragmatic problems. At that time, I guess, um, at that time you had it was the start of, I guess it was almost post-war America. So that's also a fascinating period from a sociological perspective, in the West, right? So people all of a sudden became, there was a big redistribution of wealth after World War II. People went, there was the sort of explosion of suburbs in US, and all of a sudden everybody started to have a telephone. Okay, and I think we shouldn't underestimate the societal impact of that technology, right? So the fact that everybody has a telephone, all of a sudden the connectivity between humans has increased dramatically, and of course you get different emergent phenomenon from that. But anyway, at the time, um, you know, there was, if you made a telephone call to your cousin, your girlfriend, your boyfriend, or whatever in the next town, it had to be routed through a central server where actually there was a person manually there that would kind of route telephone calls, could probably listen in on your telephone calls if they wanted to. So, I mean, people were interested in optimal sort of, optimizing the passage of this sort of messages along these lines, and these lines can be lossy. And so, what Shannon did, which was kind of revolutionary, was to abstract this idea of what is information and how do we quantify information and how can we sort of optimize information in lossy lines, right? This is really a mathematical theory developed by an engineer, which has been hugely influential in the latter part of the 20th century. I mean, there's no doubt that we're in the kind of information age now, and Shannon had a lot to kind of say about that. So that's kind of classical information theory, and there's lots of famous theorems. I mean, one of the things that he did was really define not only what is information, but also link it to the notion of the resolution of uncertainty. So if you think about messages, if you have a message like it's raining in Dublin today, I mean, there's not a lot of information in that message because it's highly likely that it's raining in Dublin today. It rains all the time. But if you told me that it's 45 degrees Celsius in Dublin today, there's a huge amount of information in that message because it's never 45 degrees Celsius in Dublin, right? So he had this idea that information is kind of like surprise, is proportional to surprisal. And there's this famous story that, um, uh, he said, look, I have this object which is called Shannon entropy, which allows me to quantify the amount of information in a message. And he went to von Neumann, who was the sort of genius of the time in computing and kind of physics. And everybody knows about John von Neumann. And John von Neumann told Shannon, because it looked like the entropy from statistical mechanics, that you should call it the entropy, because then you'll have the upper hand in any argument because nobody will understand what you're talking about, right? So, so Shannon had that sort of, he did, among many things, he kind of was the first person to think about information in an abstract way, to find ways of quantifying it and to kind of look at this from a very abstract perspective. And quantum information theory at its purest level, I guess, you can see it as being, okay, whereas in classical information theory the carriers of information are bits, so zeros or ones, then quantum information theory is essentially, allowing those carriers of information to be qubits, which can be 0, 1, but 0 plus 1, you can have superpositions. And this leads to a whole new sort of logical framework, which is sort of derived from quantum theory. And quantum information theory kind of looks to sort of answer similar questions as to what, Shannon asked about classical information theory, but now, when your sort of systems have quantum mechanical features. And that those quantum mechanical features range from, of course, superposition, entanglement, and things like that. And so quantification of entanglement, for example, was an early achievement of quantum information theory. There's very rigorous frameworks by very mathematically orientated people on how to do that properly. And so that's kind of quantum information theory in a nutshell. Um, and it's branched out into a number of different areas. It's intersected with a lot of other areas, which I think is great. So, for example, there's been a lot of kind of cross fertilization between quantum information theory and condensed matter physics. So, for example, you can use concepts in quantum information theory to diagnose various phases of matter through, for example, things like understanding how the amount of entanglement changes as you cross phase transition. Or more recently, for example, there seems to be a lot of interest um, in the high energy physics community in concepts from quantum information theory, which are useful for them. I'm less qualified to speak about it because it's not my domain, but you can see a lot of papers coming from that community, and they're interested in very similar things. For example, the kind of dual features between certain models and black holes, and how sort of quantum information can shed light on certain problems in their community, right? And then in thermodynamics, which is an area that I'm interested in, we use very similar tools sometimes as quantum information theorists do, right, to describe various different protocols, etc. Um, and I mean, that's at its purest level, quantum information theory. And then, of course, you've the byproducts of thinking like that, which are the applications, quantum computing, quantum sensing, which is the idea that you can use quantum mechanics to kind of get enhanced precision, quantum communications, which is a whole area in its own right. Quantum cryptography is a sort of one of those sort of quantum communication things. So lots of interesting kind of technological possibilities come from thinking about quantum physics like an information theorist. And it's been very valuable and hugely beneficial, I think, in general, from a technological perspective, to think about physics using concepts from information theory, which have their origin originally in Shannon, I would say. Um, so yeah, so that's sort of what is quantum information theory. Sorry, what was the other question you wanted to ask me a little bit about?
Quantum simulation.
Yeah, so I can tell you. I mean, so I basically, within my own research group, we have two kind of subgroups. We have the group of people that are interested in quantum thermodynamics, etc., which I can tell you a little bit about in a second as well. The type of projects that I'm currently working on, because I think they're very interesting. Um, and quantum simulation, we have a kind of a very particular interest in that. I mean, because of my interest in many-body physics. So many-body physics, what do I mean by that? I mean, in my language, it would be like I'm interested in models which are fairly minimal by the standard of condensed matter physics or material science. So, a material scientist would have a very complicated system. For example, they have phonons, they have multi-electron problems, completely intractable for any sort of numerically exact treatment, but they have developed over the course of 30 or 40 years, ingenious techniques and mean field theories to sort of describe matter in a kind of approximate way, which yields very accurate experimental predictions. Okay, not always works. Not It doesn't work all of the time, but for most of the things that they're interested in, it works very well. However, if you really strip down, physics and many-body physics to its basic level, you can think of more minimal models, or Hamiltonians, we say in physics, um, which have maybe the essential features of what you want to describe. Like, so you might think of a system, for example, like a spin chain, or a bunch of electrons or fermions hopping on a lattice. Um, and already those problems are difficult to simulate, right? Because of the so-called exponential scaling of the Hilbert space dimension. So if you have, n particles, then, to describe your system exactly, you need 2 to the n quantum states, right? So very soon you see there's going to be a memory problem in your classical computer to describe such situations, right? And ultimate and you run out of memory very quickly, actually, for an exact description. Yeah. And we've done a lot of work in the group traditionally on classical simulation of quantum many-body systems. Like, the best you can hope for is you do the largest simulation you possibly can, and then you try to extrapolate this to
what we say the thermodynamic limit. So we say, okay, look at the trends and see how things behave as we scale the number of particles up. So you're literally just trying to guess how things will behave as n scales large, because you don't have a computer that can kind of accurately do what we call this finite size scaling. For example, we might be interested in a particular phase transition, we might be interested in some dynamical phenomena, and ultimately you're limited using classical computers to describe this exactly, because the problem grows kind of exponentially, right? So the idea of quantum simulation, I guess, is sort of, you can trace back to Feynman, who said, that basically, why are we thinking about modeling quantum mechanics using machines which utilize classical laws? We should be building machines which are themselves quantum, and then trying to simulate quantum mechanics with quantum systems, right? So it's as simple as that. So you exploit, for example, the fact that nowadays we are building simulators, okay, which are essentially quantum computers, which are highly controllable. And there you try to write the problem you're interested onto your kind of controllable qubits, like the superconducting devices of IBM, like the ion traps in certain experimental groups or other companies. And you try to sort of simulate many-body dynamics using those machines, right? So the idea of a simulator is that you can kind of pre-program a lot of different sort of Hamiltonians of interest on the same machine. So I spend, I think, 20% of my time working with a Finnish startup called Algorithmic, which are a company based in Helsinki. And with them, we have a lot of interesting projects at the moment in collaboration. They're a software startup, but they collaborate heavily with the likes of IBM on their kind of hardware. And we're actually really doing incredible, what I consider incredible, just because I would never have seen the scale that's currently available in the lab. Like, for example, we recently did an experiment on almost 100 qubits with Abhinav Kandala's group in IBM, where we're really doing non-trivial physics on sort of various different circuit models of interest to statistical mechanics and quantum communities. And you're really in a limit where, okay, it's true that you can still find a clever classical algorithm that will do the job for you and simulate such dynamics, but it starts to become non-trivial. And my prediction is, in the next very short period of time, we'll already find problems of interest to academics, being interested in certain problems of many-body physics, which can now be sort of ported over to quantum devices, right? So we are very interested in making those simulations work, collaborating with people who have various different knowledge in things like error mitigation, and trying to find examples in many-body physics that are tractable for these near-term devices, which are not perfect. They're noisy. You have to know a lot about the devices. Um, and that is really hard work, but also very exciting and rewarding work. So that's what the group is focused on at the moment, is sort of making models which we think are tractable on near-term quantum computers, and seeing what physics we can tease out in collaboration with these sort of hardware companies. Um, and that's kind of, I would say, one of my interests in that area. On the other side, going over to the thermodynamics side, if you don't mind, another part of my group is working on various different problems in thermodynamics. I've been working on interface of thermodynamics and quantum mechanics really for more than 12 years, I would say, right? So for quite a long time. So and many different aspects in my group, but I can tell you currently I'm very interested in, I would say, two things, right, which are interconnected. Uh, well, three things, let's say, that are interconnected. Um, I'm very interested in what in non-equilibrium steady states. Let me explain to you what a non-equilibrium steady state is. You are a non-equilibrium steady state, right? So, in a sense that, I don't know, what temperature is it in the room? What temperature is it where you are at the moment? Just out of curiosity.
24 degrees.
24 degrees Celsius. So I can tell you it's 9 degrees Celsius in Ireland, but
Hmm.
our bodies are roughly at the same temperature, 37 degrees, right? So you're not in equilibrium with your surroundings, right? When you reach equilibrium with your surroundings, it's a very sad day for your family, okay? You're dead, right? So, our bodies have a remarkable sort of way of maintaining what's called a non-equilibrium steady state in the presence of sort of thermal environment. And, you can set up sort of non-equilibrium steady states of quantum systems that support a current, etc., blah, blah, blah. And I'm very interested in these states in general. When you have a many-body system connected to different baths to supporting currents. Not only that, I'm currently very interested in the problem of how you transition between different non-equilibrium steady states in an efficient way. So we're working very hard at the moment with a number of my PhD students to make a theoretical description of how you can transition between different non-equilibrium steady states in an efficient way. So the point is, by efficient, I mean you don't want to dissipate so much energy to go from one state to the other. I'm not actually sure exactly what the technological application of that is, but from a fundamental physics perspective, it's very fascinating, right? To see how you can transition between one non-equilibrium steady state to the other. And it turns out what becomes a very useful concept for us to deal with this type of thing is information geometry. So I'm very interested in the interplay between thermodynamic concepts and what's called information geometry, which is the mathematical subject which originates from studying the geometrical structure that emerges when you take probability distributions that are parameterized by some parameters. And you do exactly the same for quantum systems, where you replace the probability distribution function with a density matrix. And understanding this geometry, which is actually very important also for things like machine learning, it's not my area, right? Is very useful because we can exploit then mathematical theorems coming from geometry to understand essentially shortcuts in the space of our system. So we can understand, for example, what way do I have to change parameters so that I can go from point A to point B while I minimize the amount of dissipation? Questions like this, right? So this is one thing I'm very interested in, the role of sort of information geometry to kind of guide us in problems, in particular for states, transitions between different non-equilibrium steady states. The other interesting thing that we're studying at the moment is a 2,000-year-old problem called the Mpemba Effect, which was already studied by Aristotle. So Aristotle, what is the observation of Mpemba Effect? The Mpemba Effect is the observation that sometimes hot water can freeze faster than cold water, which is counterintuitive, right? And the name gets its name from a person called Erasto Mpemba, who was a Tanzanian student in the 1960s, who basically was in home economics class as a schoolboy in Tanzania. They were making ice cream, and when you make ice cream, you have to heat sugar and milk solution. And he noticed where all the rest of his classmates have waited for their solution to cool down, then put into the freezer. He put his hot solution into the freezer, and it cooled faster than the other students, right? And so he said this to the teacher. The teacher said this is nonsense because it violates Newton's law of cooling. But he kind of persisted, and a physicist visited their school in the 60s and basically did some measurements and confirmed that, yeah, there's something to this, right? And currently we're interested in the Mpemba effect when you apply to quantum mechanical systems which are thermalizing, right? So, and I'm actually very interested in, again, in the connection of the Mpemba effect to the geometrical structure that occurs in the dynamical system, right? So can we understand Mpemba effect geometrically? What are the kind of consequences, etc., and how this links to information theory and quantum information theory is something that we're actively working on at the moment, right? And I think it's a it's a good problem because it makes you think about how do you speed up cooling, right? Which is actually a very pragmatic problem. Cooling is difficult, right? And cooling is something that's highly desirable for experimentalists, right? They need to cool systems down, and if they can do it quicker and more efficiently, that's better. So that's really current projects in the group that we're working on at the moment. So these type of topics.
Just out of curiosity, you were studying the quantum aspect of the Mpemba effect. Is there
Yes.
any classical explanation to it?
Yeah, this is a good point. So actually, I would say that it's been a kind of topic of controversy for the last period of time, right? So, it had been observed by people like Aristotle, Descartes, Bacon, other people in history, but just observations. And then the first sort of rudimentary experiment was performed in the 60s. And then there was a big debate for decades, really, as to whether it really existed or it was just a particular example, it wasn't universal, etc., etc. And then there was some breakthrough, relatively recently for classical systems, where at least mathematically you could understand why this was occurring. If you have a model for your system and your model has what we call decay modes, if your initial state has a cancellation with the slowest decaying mode, then in principle you can get this Mpemba effect. But actually, from a physical perspective, it's still a bit unsatisfying because we don't really have any good idea of to why this occurs from a physical perspective. Like, if you give me a system, I can't say whether it will have an Mpemba effect or not. All I can tell you is if you give me a model which accurately produces that, then maybe I can mathematically tell you that if it occurs or not, right? So it's an interesting one, and I think it's unsatisfactory. Like, it's not really, which is good. It means we still have work to do. People don't understand it well. They understand certain aspects of it, um, at least mathematical aspects, but I think the physical understanding of it is still relatively poor.
But no, really, really interesting. I mean, not just this, but like also the other facets that you are performing your research upon, whether the thermodynamic side or the simulation side, as you previously mentioned.
Yeah,
But
sometimes,
that,
as I said, sometimes those topics intersect. For
hmm,
example, in many body physics, you know, if you have dynamical evolution, right? So if you're really looking at something dynamical in many body physics, it's an interesting question that a lot of people are interested in, is how systems that are isolated, like a Hamiltonian system, thermalize. And that those questions, people have been asking those questions for a very long time, since Schrodinger and von Neumann. There's been a lot of experimental breakthrough in AMO physics which allow people to sort of manipulate these systems, and study dynamics over very long time scales. um, and there's all different facets to that problem. These are things that we study in the group, like things like eigenstate thermalization hypothesis, etc. But also we're interested when that sort of issue, when you have like phenomenon that may in principle break down this so-called uh, thermalization process, right? So things like weak ergodicity breaking. It's a bit technical, but when do the laws of when do the laws of thermodynamics struggle, to emerge? These are also interesting things for my group. And then you have the intersection between the two areas: thermodynamics on the one side, which describes thermal behavior, and many body physics, which describes the dynamics of many systems. And whether you do that on a classical computer or on a quantum simulator, it's up to you. The big advantage of a quantum simulator: larger system size. The big disadvantage is that actually the systems are noisy and they don't survive very long, right? Like, you have to understand that they're limited in how long you can study the dynamics of a system for. Whereas in a classical computer, you're limited by system size, but you're not limited by the length of time. Well, to a certain extent you are, but because of the system size being small. But yeah. So there's all sorts of interesting problems there, which kind of lie at the interface of many-body physics and sort of statistical mechanics as well.
that would really bring me about to ask you the role of industry academia partnerships. You did mention that you also work with startups. So you mentioned one. How do you feel it's important, seminal, and to what degree does it help forthright progress and make advancement into certain research areas?
Yeah, I mean, this is a very good question, right? Because I think this is very unique at the moment in I mean, sure, it's happened in other areas at different points in history, like in, I don't know, quantum dots when they were trendy, and machine learning to a certain extent, and different things like this, right? But yeah, so the I think it's positive. I mean, the thing is that there's a lot of speculation at the moment, right? It's in particular in quantum computing, right? Um, where you see many of my colleagues who work in that area maybe have left partially their positions to work in the private sector, or maybe to start a startup. Um, I think what that does is it focuses the research a little bit. Of course, it's precarious, right? In the sense that in the university, the idea is that you should be free, in a sense, to do what research you want to do, right? And that research doesn't necessarily have to be relevant, right? I mean, what does it even mean? I mean, you should have the freedom in a university to do what interests you, as long as it's of sufficiently high quality and the university keep paying you. I mean, you're kind of happy with that, right? Um, in reality, maybe universities put pressure on people to work on more applied things because it's easier to get money, etc. But in principle, the university, you should be free to work on what you find interesting. And I think if we abandon that model, we're really in a bad place in science, because I think innovation at its core, I mean, at its fundamental primordial level, really emerges from that academic freedom. Um, Whether it becomes irrelevant from a sort of applicative perspective after is irrelevant, right? I mean, you still have to have that initial curiosity driven science, and I think I'd be very reluctant to give that up. On the other hand, you know, because the weird thing is, public universities, in my mind, have adopted an industrial model of late, at least in the Anglo-Saxon kind of world. And I think that's very bad, because they start to behave like bad businesses sometimes, right? Where they try to treat their kind of people as, sort of people that generate, I don't know, like kind of innovation, right? And I think they drive innovation by default, even just by doing fundamental work. It's a natural byproduct. Um, so I think a lot of people get kind of annoyed, academics get annoyed by this, and they said, well, look, if I'm going to be like that, I might as well make more money and go to the private sector, right? Um, One advantage of the private sector is you don't have I mean, the bureaucracy, let's say, that's typical of universities now is sort of stripped away, and you have people which are taking care of that, not the academic themselves. And the researcher in the private sector can often focus a little bit more on their research, right? They spend more of their time. They don't have to teach. They don't have to do a lot of admin. They don't have to mark papers, any of this kind of stuff. They focus on research. However, the research is dictated by the company, right? So you're not as free. So this is the difference, right? For a thing like quantum computing or quantum technologies, where there's a clear kind of goal to make fault tolerant quantum computing work, to find applications, I think it's necessary to have both. You need people in the academia doing off-center kind of ideas, which may lead to something, and you need that sort of drive and financial stimulus of the private sector and focus to progress things. Okay. However, we all know in the history of technology, no matter how many roadmaps you put in place, whether that's at a kind of government level or whether it's within a company, a roadmap is never a roadmap as you expect it to be. I mean, a good example is computing, right? I mean, prior to the invention of the transistor, people were doing computing with vacuum tubes, punch cards. I mean, if they built a roadmap, they certainly wouldn't have been able to see the invention of the transistor revolutionizing their field. And ultimately, you know, something like that could happen in the quantum computing story, where there's a sudden moment where a new technology emerges, possibly from off-center thinking in a university, and all of a sudden you're in a different paradigm and everything accelerates much faster than what's been sort of predicted from some sort of linear extrapolation on a company boardroom, right? So we should take them with a pinch of salt, right? Like, but I think you need both. You need people thinking crazy ideas, being free to think about the things they're interested in, whether it be in the private sector or in academia. And you also need that sort of directional, sort of incremental improvements on the research, which comes from a focus and financial stimulus. So I think it's important to have both. That's my answer to the long-winded answer to the question. And then we
Mm,
need
mm,
we need we need different we need more diversity in terms of the personnel as well, because I think the more diversity you have in terms of the way you think, the way you are, different types of people, the more chances you have of innovation growing. You know, that's the way I understand it, or at least from my own experience.
How significant do you think is mentorship or the presence of a mentor in the scientific realm, the scientific pursuit, and for the professors and the teachers out there, what according to you is would be a better approach to guide this up and coming generation?
So, I mean, let me answer. I mean, mentorship for me is something I take very seriously. I've had many really good mentors along my career, which I'm very grateful of, and I don't think I would be where I am now without them. It's not something you stop, right? Like you have mentors at different stages in your career, right? So obviously, you know, I had very good PhD supervisor, would have acted like a mentor in my earlier career, and then various different people when I was a postdoc, not to name any names, played different roles at different times in different ways as mentors. Like, so whether that's dealing, you know, with stressful situations at work, whether it's, you know, how to deal with a major factor in academia. I think we often talk about our achievements, but, you know, academia is a place where, you know, you have a huge number of failings. Um, and I think people don't often talk about the amount of times they fail. Like, the amount of times you have failures relative to your successes are much higher, right? So I always teach my students that you have to develop resilience and don't take things personally. This is just the nature of the game. I think the difference is that your failures in academia are often broadcasted, right? So, you know, if you don't get a grant, if you don't get a job, people know about it, right? Like, or somebody criticizes a work of yours or something like that. You have to develop a thick skin. And I think mentorship is very important to let people know that it's like, it's a bit like, you know, if you think about social media, right? So everybody has Google Scholar pages now, you know, they tweet about the research. Of course, they only tweet about the good things. I mean, you don't have people tweeting about, I just failed on a grant application today, or we don't have a Google Scholar for the amount of grants we submit and don't get funded, right? But those things are actually existing. And I think younger scientists, they often get dismayed by the fact that they're only ever seeing the amazing achievements of others, right? So they have this tendency to kind of get anxious when they sort of look and judge themselves against their peers because they only see the great things. But what they don't see is that behind every success is multiple failures, right? So mentorship from others has taught me to think about that in a more rational way. And I think that's hugely important to make the right decisions, and in particular to manage your own expectations, right? So I take mentorship very seriously. I consider myself to have a good record in mentorship at different levels with postdocs, with PhD students, etc. And I think that element, that human element in science, is often we don't talk about it, but I think, you know, often we don't give enough credit to mentors. Like within our, we don't reward good mentors enough within our systems, right? We kind of reward people for their amazing achievements in academia and research, in teaching, but how do you quantify someone's ability as a mentor? I guess you should look at the happiness and you know, sort of eventual trajectory of the people that work with them. So it's hugely important, right? So my advice to younger people entering academia, whatever kind of in whatever field, is seek out mentors, good ones, and strip away toxic people from your journey, right? You're always going to get people in every walk of life, and in particular in academia, which maybe have a chip on their shoulder, have become disgruntled. You have to try and strip away that negativity, right? And find positive people who will help you through and help you kind of fulfill your kind of goals, because ultimately it's a great privilege to be able to be an academic, to be able to work in research, to be able to work on things that you're interested in, to wake up in the morning and do a job where you'd actually like, right? So it, and don't take yourself so seriously either, right? So I think there's a tendency as well in academia for people to take themselves really seriously, but on the grand scheme of things, what they're doing is not really important. Like, if they don't do it, somebody else will do it, right? So you should do it because you enjoy it, you find it fulfilling, and you shouldn't really think that what you're doing is so important. You should just do it because you love it and enjoy it. And I think if you can take that sort of perspective, inevitably you'll be successful in any walk of life. Yeah.
How do you find how do you find good mentor? How do you approach them? How do you know at first if somebody would be a good mentor to you?
Yeah, so I don't know. I mean, I've actually, I mean, I still have a fellowship from the Royal Society, a URF. I'm in the latter stages of it now, but they give very good training. And I was recently at a mentorship, um, sort of, let's say, meeting about how to be a good mentor and how to deal with mentees, etc., like that. And I find it always very interesting because, you know, I think it's not really just a one of course it's not just a one-way interaction, right? So I think the mentor and the mentee have to be right for each other. It's not necessarily obvious. Somebody could be a very good mentor but maybe not the right mentor for you. Okay. um how you approach people to be one, yeah, I mean, that's an interesting question. Like, the Royal Society, for example, have a scheme where they pair people up, right? And they try to kind of engineer it, and it works pretty well more often than not. But in reality, if you don't have such a system, kind of mentorship arrangements often kind of happen organically. And it's a good question. How do you find one? I think you just have to try out different people and see if they're willing to kind of participate. And honestly, it's a two-way thing because the mentor has to get something from the mentee as well, right? Like, so, and often you find that like the best mentors get, like, I learn a lot, for example, from, in particular, from students, both scientifically and also just how to think a little bit differently, right? So the worst type of a boss is one which imposes themselves completely on the relationship and tells people you have to do it this way. I think you should be open-minded to another way of doing things always, right? And maybe kind of, sort of rationalize together, try out different things together. um because I think if it's one way, it's not enjoyable. In any way, you don't really progress. Like, if I say, no, this is the way it's done, I mean, how can you ever see an innovation coming from that type of a relationship, right? You need to learn from each other. It's not easy, I mean, to find good mentors, but they do exist, and I've had plenty examples myself of that.
Again, I completely agree with you. It is a thing that cannot really be fabricated or synthesized. It if it's bound to happen, it'll happen organically, and you'll just find them. You'll just fall upon them. And also, it's very significant to remember for anybody who's seeking out a mentorship from somebody. You must be willing and competent enough to be adding value to them or their work.
Exactly, exactly. That's exactly true. And I think, this is a discussion that sort of transcends any scientific or academic thing. Could be in business or whatever, right? Like, it's a more of a kind of life lesson. And I think I'm very I'm very keen on not only like mentorship, coaching, stuff like that. I think in general in your professional career, um, it's very important for self development, right? Like, so. Um, I mean, there are rare examples of people who don't need anybody else, but they're rare, right? I mean, people rely on each other often than not, right, for different things, and it can be can be totally. I mean, you know, it doesn't necessarily have to be about work all the time, right? It can be about just different things in life, how to cope with living, which is something that we all have to cope with, like. Um, and then, you know some people are more experienced in certain aspects of life than others, and I'm sure mentees are more experienced in other parts of life than their mentor in some cases, right? So we all have very different and diverse backgrounds, and I think we start respecting that and learning from each other, I think, can be very powerful.
There is a very different culture regarding the perception of any domain, but since we're talking about science and technology, then that with the shift in geographical demographics and this certain shift in distinction or difference between the cultural perception of research and science often leads to the kind of advancement and progress that a nation will be able to make. On a broader scale, holistically speaking, what do you think is essential for any country to make scientific advancement, and to the extent where they are able to contribute globally to the upliftment and elevation of science and technology?
Yeah, I mean that's a very difficult question, right? Because it has multiple facets, right? I mean, first and foremost is really bread and butter stuff. Like you need to have a good um, and easily accessible education system. So, I think nowadays as well, um, which is sad but true, I think the way that globalization has gone, the standard of English has to be very good, right? So it's more difficult, I think, to succeed in a globalized picture if you don't have English. Now there are ways of doing that, but it just unfortunately is the way that the world has gone, and people have adopted in the global sort of globalized world English as the first language. And I think an easy, accessible public education system that's sort of accessible for everybody, irrespective of their background or sort of income level, is first and foremost primary, right? Like so, you need this first and foremost. And then I think you need, again, at all levels, right? This has to be at primary level, secondary level, universities, then, right? So this is the difficult part, right? So I think you could have the best, most outstanding high school students. And then the issue in universities is that, like, you need to develop a culture, which is not easy, of high level research in the country, right? So that's respected, right? So even in Ireland, where you think it's a kind of a very sort of hyper industrialized kind of modern country, like I often find sometimes there's a perception of what university lecturers are just teachers. So, whenever I say to people in the summer, they say, "Oh, you're off for the summer now because you're not teaching." I say, "Well, actually, teaching is only a percentage of my job. My main job is as a researcher." And I think there's almost there's a public perception of even in Ireland where sometimes like it frustrates me um, that people don't really understand what researchers do. We could be guilty of the fact that we don't do enough public engagement ourselves for that, but that is the truth. Okay, so I mean, you need to develop a research culture within the country that you're in, so that you have people in the universities then which are able to teach these talented people interesting things and how to do research in a modern way. Now that is the difficult part, right? Because if you don't have that, what happens is brain drain, right? You have a country which has fantastic graduates at secondary school level, and where do they go? They might do an undergraduate degree in their country, but then they go abroad to, sort of a place where the universities are very kind of prestigious, and they never come home, right? So one way, and I'm thinking about like the likes of India and China and these places which have unbelievable sort of graduates, and many of them go to the US, etc., and maybe stay there. I know there's plenty of good people in faculty there as well. Um, but maybe one thing that you can do, I think, is try to incentivize the top talent that have been educated abroad, for example, to come home through financial incentives, right? So you give them a big grant, starting grant, you lower their teaching load, and you start to bring back excellent people to work in the universities. And then I think you need some sort of system where entrepreneurship is, and this is tricky as well, right? So there's research and sort of academia and all that, but then the kind of innovation, kind of the growth of the innovation sort of system is not easy, right? So you might say, how do we convert this example? I might be interested in having lots of companies and startups and all of that. Then you need to incentivize entrepreneurship in a way that people aren't afraid to fail. And I think whatever criticism people have about the US, they get this right? So it's easy to be an innovator or an entrepreneur in the US. And you know what? If your company fails, big deal. You get up, you sort of pick up your bag, you go again, and you start again. And many people who've become extremely kind of successful in that domain have failed multiple times before they actually, succeed. And having that sort of culture in a country is difficult, right? Because it can be just culturally not the done thing, or but it somehow you need that, and also then you need this other aspect, which again is important. You need people within the country who are in that sort of research environment who maybe played a role as lobbyists to the government, because let's be honest, often governments have no clue what goes on with research. So you need some strong personalities basically to knock on the door of people who actually supply the funding and say we need to do this and we need to do it like this. But again, there's no straightforward answer to this question, but these aspects are somehow basic enough that they need to be there so that you can compete on a global scale. Yeah,
Oh, I agree. Any population of any country is as good as the output or value that they are able to generate. Otherwise, they are just a mass of latent energy, which
yeah,
becomes underutilized, and then they are to certain degrees compelled. When you talked about brain drain, right, they are compelled to move out to pursue better opportunities to
yeah,
be able to paid at a significant level, right?
yeah,
But that again ties back to, because I can speak for India. From for There has been this emphasis on these two domains specifically, research and entrepreneurship, and it really tilts the perception of especially the young minds, the people in high school or middle school, how they start envisioning what they want to do for the future. And the other aspect that I think becomes again very fundamental towards driving this growth is the sentiment of nationalism to a certain degree. With countries like Ireland, India, and these places, they have this cultural sentiment of nationalism, a collective being, right? Whereas countries like the United States, you'll find that at these research levels or these higher end education levels, there is a lot of populace which is not by background natively from the US, and which is why the Americans sort of, they are now starting to focus upon pushing this nature of this sort of culture that became prevalent there, of entrepreneurship, but like not in scientific terms. So
yeah.
they are starting to pivot it towards research and technology. So that again is a very fundamental thing that you need to cater to and strike that fine balance between
Yeah,
entrepreneurship and scientific technology.
yeah, and I think that's it, right? Like, so, I mean, you also need, universities for me are best public, right? So in my mind, you shouldn't have to pay exorbitant amounts of money like you do in the US to go to university. It should be accessible to everybody. And then there's a fine balance between having that type of a system plus also having a sort of innovation system that allows, sort of easy start and fail of startups, which is very liberal, right? So the idea in liberalism is that you pay for everything, but like you need somehow a combination of that sort of state where we say, look, education is sort of free, accessible, etc. But we also want an innovation system where people are allowed to make mistakes and start again, right? So getting this sort of as a fine balance, and I don't even know what you'd call this, sort of structure, but somehow some balance between the two of these would be the right way in my mind. Which is neither on the left or on the right. It's somehow very right wing in some way because of but also very left wing in another, right? So it's kind of difficult for me to put my finger on it, but I feel that that's sort of the natural thing to do is like invest a huge amount in having easily accessible, give everybody a chance, right? That independently of their background, and then allow people to fail and support them if they fail and allow them to start again, which is very liberal, right? So I don't know, like, because often the countries that invest a lot in free education, etc., are very careful when it comes to innovation, and that stifles innovation, right? So you kind of need that sort of balance in my mind, I don't know if any country has got this completely right, you know. So um, yeah.
It was a delightful conversation, and there is this final segment that we do on the show. What would be your word to humanity?
My word to humanity. Well, I mean, look, we're in a we're in a very strange period of time as humans. But then I say that, and I look at the news, and it's terrible. You know, you see what's going on all over the world. I don't want to mention certain things that are going on, but we all know, and like you're saying, you know, the amount of human suffering seems to be kind of constant. But I suppose that this has always been the case all through the history of humans, and you know, I don't know. My main to people, I mean, I think in some ways maybe the hippies had it right in the '60s, you know, and we should have listened to them. I think we should be lovers and not fighters, you know, like and try to live together. Um, in a kind of peaceful way, because I don't know. I mean, is it really, you know, life is precious. Human beings are capable of amazing things. They're also capable of terrible atrocities. And I think that everybody should get along. And maybe I'll put it like this. Like I said earlier, maybe the key is let's not take ourselves too seriously. So like, when you start taking yourselves too seriously, your country too seriously, I think bad things happen. But that's very easy for me to say, you know, as a relatively affluent Western white male, like when you have so much sort of inequality in the world, right? Like, I don't know. These are very difficult. It's difficult to be hopeful now, I think. But then I think to myself, was it every, you know, you can choose to be right hopeful. I think there's been periods in the past in history which have been desperate, and you know, there's certain aspects of living now are much better than they were before. I mean, you only have to think of modern dentistry. I mean, this is already enough for me to not want to live 100 years ago, you know. So, you know, imagine what it was like to get a tooth removed 50, 60 years ago. It must have been terrible, right? Like, it's like, you know, so I don't know. I mean, I think people should just try to relax, try to enjoy themselves, and you know, we're all trying to live together in a kind of harmonious way, at least, and get on with it. Like, you know, we're all on the same journey anyway, you know.
Dr. John Gould, thank you so very much. Thank you for being on the show and having this entire conversation.
Thanks a lot. Bye bye.